All right, as requested, here are some helps with the alum analysis lab that's due on Thursday. Um, we did 2 tests to analyze the purity of the alum that you made in your synthesis of alum lab. One of them was the melting point test. I bolded the formula of alum in the introduction because that will be helpful for you in the second part. I bolded also the accepted value for the melting point of alum, 92.5 degrees Celsius. That will be helpful for you in the first part. And then I've highlighted on the calculations table where the answer should go. I was asked, do you need to put the calculations table in your lab report? And the answer is yes, absolutely. It does say that as part of the questions. Notice it says you need to show an example calculation other than the averages, and you need to put your results in the calculation data table. There are 2 calculations where they will not need to go in the data table. I'll point those out as we go through it. Make sure you follow your sig fig and rounding rules, include your units, and round your percentages to 0.1%. Okay? So the first one says calculate the percent error of your melting point test. Use the average of your 2 trials as your experimental value. This does need to be reported in the calculations data table. If you had a range of values for your melting point temperature, you may use the midpoint as your temperature that you calculate an average with. So let's say that your sample melted between 90 and 94, then the midpoint would be 92. If it melted between 90 and 100, the melting point would be 95. So use that middle value. I will tell you, typically the smaller the range, the more pure your sample is. But that's just more something you get into in organic chem. Percent error, you don't have to show me the actual, I put out what average melting point is question 1. You do use the average melting point to do number 1, but the percentage, percent value will not go here. The percent error does not go in the table. Just the average melting point goes in the table. Okay. Number 2 says calculate the mass of the alum sample before and after heating. If you look at your data table, you have the mass of the crucible cover and the alum before heating, and then the mass of the crucible cover and alum after heating. So you want to tell me how much alum you had before you started heating it with the Bunsen burner, and how much you had after. That should be pretty straightforward. I only need to see 1 calculation for each. And then it says calculate the mass of the water that was driven off during the heating. You actually have done, if you go back to your determining a chemical formula lab, you've done something like this before. If you notice in part 2 of the calculation table, I said before heating you had a hydrated alum sample, which means that you had the water as a part of it. Sorry about that. Snow is being feisty. And then you had the mass of the alum after heating when all the water had been removed. So you were left with just the part that was before the dot. The 12 molecules of water for every 1 unit of the alum salt had been heated away. It had turned into vapor. So if you know the mass that you had before with the whole molecule, and you know the mass that you had after with just the salt part of the hydrate, you should be able to use conservation of mass to determine how much water was driven off. Show me 1 calculation, and we're good to go. Make sure you record those answers in your data table. 4, 5, and 6 are taking your answers for 2, 3, and 4. Sorry. For 2 and 3, the mass of the alum before and the mass of the alum after, as well as the mass of the water, and figuring out what the moles are for each of those. The hydrated alum, again, it contains all the water, so make sure when you do the conversion for that, you include the molar mass of the entire hydrate, while when you do the moles of the anhydrous alum, that you do it just for the salt part, and then use just the molar mass of water to do the conversion for number 6. Again, show me 1 of those calculations, put the data for both in your chart. Number 7, determine the ratio of the moles of water to anhydrous alum for each trial. Round your answers to 1 decimal place. So you have the moles of water in number 6. You have the moles of anhydrous alum in number 5. Divide and round your answer to 1 decimal place. Hopefully it'll be pretty close to 12, since that in theory is how much water you had according to your chemical formula for every 1 unit of the salt. Okay? Calculate the percent error of your ratio using the coefficient of water for your accepted value. So there's 12 water molecules. Your ratio is going to be your experimental value. You may use the average of the ratios that you calculated from number 7 as your experimental value for number 8. That calculation does not need to be reported in your chart. You do need to show me your calculation. There's only one calculation for number 8 since you are using the average ratio as opposed to each individual ratio. Number 9, calculate the percent water in your alum sample for each trial. So water is part of the alum, so part over the whole. You have the mass of the water from number 3. You have the mass of the alum before you heated it. That was the intact alum sample with the water included. So divide the 2 times it by 100 gives yourself a percentage. You should do that for both trials. For number 11, the theoretical, there will only be one value to calculate for that. That's because you only have one chemical formula for alum. And so that's why you notice up here that the theoretical does not have 2 spots. I skipped over 10, sorry about that. 9 is the percentage of water for each trial. 10 is just the average of those 2 values. So that should be pretty straightforward. Number 12, doing another percent error. You have the theoretical value from number 11, that's your accepted value. You have your experimental value based on your data from number 10, and then calculate a percent error for me. Number 13, how confident are you that your sample is pure alum? So what did your percent error data tell you? How close were you? Typically, if you're under 10% error, then you can feel fairly confident that what you got was accurate. If your percent error is like 10 to 15, I'd say probably you're fairly confident. If you start getting much over 15, really can't be super confident of how close your alum sample was to being pure alum. So when I'm talking about discussing the accuracy, I'm asking you to discuss the percent error calculations. You've had 3 of them, 2 for the percentage of water, and then 1 for the melting point test. And then think about possible sources that going back to the synthesis lab. What were reasons that you might not have made as pure of alum as we would have liked? Why wouldn't I let you use this as a spice at home? 14, suggest other tests that can be conducted to verify the composition of alum. So think about other physical properties of alum that we could examine. Physical properties are anything any sort of property that could be measured with your senses, any sort of property that could be measured that doesn't cause a substance to be transformed into something new. So you could do that. If you research chemical properties, you might be able to come up with something there. Because we're dealing with purity, you're typically sticking with just physical properties. 15, if the melting point test was the only test you conducted, how confident would you be and explain? So using just your melting point alone, would you feel fairly confident? Or do you feel like additional information would be helpful to verify? Keep in mind with that, obviously the more data you have, the more conclusive of a decision you can make. So I hope that helps, and if you need anything else, ask me in class.